So in general relativity, parallel transport is a theory that describes the paths along which particles move. Every particle can be ascribed a certain tangent vector or a tangent arrow. And the paths along which particles move have these arrows parallel along the entire length of the path. You can see in the top left image that a non-curved path or straight path that is not affected by gravity and a curved path that is affected by gravity both have tangent vectors that are parallel along the entire length of the path. This is what defines the path that particles move along. This may seem a little bit abstract, but it makes more sense when we consider how particles move on a surface. So for instance, if I'm standing on Martin's Way and I have a bowling ball and I roll the bowling ball down Martin's Way, which is flat, the path of the bowling ball is going to be straight. But if instead I roll the bowling ball down College Hill, the curvature of College Hill is going to curve the path of the ball. But what does this mean for the arrow? Well, we can use what's called a parallel transport machine, and a small handheld example is shown in the bottom left. And the pointer on top acts as the arrow. The parallel transport machine takes information about the curvature of the surface and transfers that information through the wheels through a series of intricate gears to the pointer. My thesis has been to construct a human-scale version of a parallel transport machine. You can guess what I used for that. The physics department owns this adult-sized tricycle, and I've modified it to act as a parallel transport machine. So if we follow the path of the bowling ball as it rolls down Martin's Way or down College Hill, the virtual arrow that this machine produces is parallel transported along that path. So the way that this works is that there are two electronic sensors that monitor the distances that the wheels turn, and then that information is sent to a computer, and that computer spits back at us the angle at which the arrow is pointed. We can measure some really interesting topographic properties using this machine. For instance, we can find the paths of fastest ascent and descent up a hill. That would be like the path that the bowling ball follows as it rolls down College Hill. And if we enclose a loop, we can measure the average slope and curvature of the surface that we've enclosed. One of the most interesting things that we can measure, I think, is actually the curvature of the Earth with a machine like this, in theory. The scale of this machine is not quite big enough to do that. We need to enclose quite a big area in order to compare the initial and final positions of the arrows. But I think that that's really profound. And a final note that I have is that things in general relativity are notoriously difficult to measure. But the fact that we can measure something so fundamental to our universe using a tricycle is pretty profound. So thank you.